So let me start the next lecture. So we will do some today we will do something on composite of two fields. Okay, or composite. So composite field means, as the name suggests, it is a composition of what? Of two fields. Suppose you are on K1 and K2, both are from F. So I am writing in this ink. So suppose over a fixed field F, there are two extensions K2, and both are contained in both are subfields of a bigger extension, which is K. Then the composition of these two things are defined as the smallest subfield. See, if these are subfields of K, then K contains both K1 and K contains both K1 and K2. So K is a subfield that contains both things. But what is the smallest subfield? See, K is there, but can we reduce K in containment so that it contains both K1 and K2? Okay, so that gives the concept of composite subfield. The composite subfield of this and this is denoted by K1, K2, and it is defined to be the smallest subfield. So let me write down. Let that is definition. First, let me write definition. Composite field. So let K over K1 and K over K2. You don't need ground base field if here. No rules. Then composite field K1 and K2 is defined to be the smallest subfield that contains both things. Subfield of whose thing? Subfield of K. K2. It is denoted by K1. It is notation. Okay. So let me do some examples of composite subfield. So one classical example is the so we are looking exercise. Let me in the question. So the composite field the composite field is not subfield of Q, it is square root of 2, it is cube root of 2, and this, what is the field we need to determine? It is, I mean, okay, is Q 6 root, that we need to prove. Why? Because observe this thing. First of all, if we do square this thing, that is this thing. So this thing lies inside this thing. Because I am getting the generator, okay? So I can directly conclude. This lies in this because it is the fraction. And each fraction where these things appears, I can write it as this thing, this square. I can replace this by these things, but these things, polynomial is this, belongs to this. So one containment is thing. Similarly, also root square equal to sorry, it cube will give you implies that in the other words you can, I mean, also how to manually verify this. I mean, what is the natural element of this? A plus b root 2. Now we can write this a plus b into root 6 whole cube. So that is inside this thing. That is another way. And for this thing, how any element can look like? A plus b cube root of 2 plus c cube root of 4. But I can replace this thing by this and this thing by this square. Same technique. Just wherever you look, you find root, you will replace by this and take the whole thing there. Okay. So one inclusion is correct. So this thing contains this and this. Okay. So why it is smallest? It is smallest. I need to show it is smallest subthing that contains both things. Let F be any field from A. Sorry. If how to say smallest? If F is any field that contains both Q root 2 and Q cube root 2, then inside F I will find this thing. I cannot get something. So if any field F is any field, so inside field that I need to show. So it is the smallest. Okay. It gets inside any arbitrary field that satisfies this. So it is the smallest. I cannot go further this. This is the trick to show smallest. Then F contains this thing, they are quotient. So F contains this. So in particular, this thing belongs to F, and these things also belongs to F. So F is a field. Field is closed under division also. So this by this will also belongs to F. That means this is to the power 6 to the power. Therefore, it also gets inside it. So it is the smallest subfield. Smallest field that is, it is a composite field. Don't need to write that. So it is done. Now, now there is the extension, field extension. So now suppose K1F and K2 over F are field extensions. Finite extension, okay. Assume K1 comma F. Hold on. This extension degree is finite, so assume it is generated some a finite dimensional vector space. So let n and F basis be an F basis of K1. Also assume it is again K2 by F is finite, so let M and also let F this is K2. Then what is the subfield then? K1, K2. What is K1, K2? That is the smallest subfield. So that will be this thing. Just check. That means I can say that it is actually field generated by K2 over K1 or field generated by K1 over K2. You can roughly think this. Okay. You can roughly think K1, K2 as this. But if this is reducible, for example, alpha 1 and beta 1 are same, then I can further reduce this. I don't need no need to write them twice. Alpha m, then start from beta 2 to beta m. Okay. I am not saying this is reducible. I mean, this is the redundant. This is redundant. I am not saying this is, I mean, they all are linearly independent. They might be linearly dependent, might be same also. Or F linear, suppose alpha 1 is F linear combination of beta 1 and beta m. Then remove alpha 1 or remove the, then, sorry, remove alpha 1. Okay. So That is the thing. So it is basis. So any element of K1 K2 is F linear combination alpha I and beta j. Okay. Note that K1 K2 is spanned by this set. Sorry, spanned by sorry, it is n. But as we don't know about this set, I mean linear independency. Linear dependent over F or not, we cannot decide about the basis. Okay. So that means spanning set. So basis will be a subset of the spanning set. Okay, it might be equal, might be not equal. So therefore, K1, K2 over F, that is there. You can say that is by Tower law. That is the product. That is the same discussion, right? You can directly write. Okay. I mean, this also comes from this thing. This also comes from this thing. That is f of alpha I and beta j's over f of alpha i's. Alpha i's means all alpha 1 and into f of alpha i's over f. But we know that is m. But I don't know about whether these beta I, beta j are independent over, they're independent over f, but they might be dependent over f alpha I. So that might drop by, that is n, so that might drop from n according to their linearly dependent or independent. Okay. So I have told everything and we can write the following proposition. That, that extension of f, then we know that extension is finite and that is less than Then we have again the proof. Proof is simple. What I told, I am writing. Now K1, K2 colon F is, what is this? This is actually F of alpha 1 dot alpha n beta 1 beta m colon F alpha m into F of K1. Okay, sorry. This is suppose K1 and K2 is, I have to take it as K1 as finite extension. So I am again writing and K2. Now this extension we know. Degree of extension is uh, n. So write all, while I wrote n. But what about this degree of extension, right? This degree of extension. Now the degree of extension simply depends on again the tower laws. So first tower in, I am attaching this with B1. In the next tower, I am attaching, so in the first tower I am doing this thing, tower. In the next tower I will do again one element. So inductively adding, we will get finally this. So the degree of extension is multiplicative of degree of the smaller extensions. Degree of the smaller extensions. But degree of smaller extension, we have no idea. No idea about this. But uh, but this thing, and hence the proof follows. One thing, equality holds if beta 1 to beta m, they are also independent over this thing. I mean, independent, then the degree will be same. I mean, it will. I mean, it will at each step, or in each step. I am not. Yeah. It is vector space basis. So degree, if they are linearly independent. Okay. So no tower here. So if they are linearly independent, then this is a basis. and this is a spanning set of less than equal to m and they are linearly independent, so that forms as a basis. Why they cannot be more than m? They cannot be more than m because I started this set at finitely. Okay. So one special case. Ready? So you know the old notations here, right? A1. So if GCD of equal to 1, so I mean they are co-prime. Then that is exactly multiplicative. Right? What we have seen above is K1, K2, colon A, that is less equals to K1. Okay? That we have seen. But K1 colon A, that is, I mean, from the tower divides K1, K2 colon F. Why? I'm writing because it is is K1, K2 colon A equal to K1, K2 colon K1, K1 colon. So it is a factor of this thing. It is both, everything is integer. This is an integer, this is integer, this is integer. So, I mean, this is a factor of this, that means it divides this. Similarly, if I take the tower K1, K2 colon F, first I take K2, K1, K2 colon K2 over K2 colon F. Similarly, from this thing, I can say this divides this. Similarly, but observe that if this and this divides this, and they are co-prime, so the product will also divide this. Okay. But GCD of A1 colon F, A2 colon F, that is the degree of extensions, it is 1. Thus, the product will divide. Product will divide means what? This is this thing divide. So I mean this integer must be greater. So combining, so the converse inequality we have got here. Here. Now this, so they are equal because this is less than this and this is less than this. So combining two inequalities, say They are equivalent. That is the thing. For an example, what is the composite degree? Degree of composite field of Q root 2 and these things. So I have calculated this is Q root 6 2. So over 6, it is 6. I can calculate also this formula because this degree is 2, this degree is 3. So 2 into 3 are therefore prime. So this degree is 6. So the degree I can guess also from there. So I want to conclude my class here. Thank you for your attention.